Hello everyone, welcome to week recitation. So in this recitation, I'll be reviewing the chapters 6 and 7. So we'll go through the dislocation and strengthening mechanisms and then the failure. This is like a quick revision or like a small preparation for your in class test 3. So let's go through that. I'm just using the slides that were slides of posted for the lecture notes. So using those slides, I'll just quickly go through them. So for this recitation, I'm not posting any other extra notes in the recitation section. You can just go through the PPT slides and the notes that you have. So first to start with, we have the dislocation and the strengthening mechanisms. So first, we have two types of dislocations, edge dislocation and screw dislocation. So this edge dislocation is like missing of a plane of atoms or the presence of an extra plane of atoms. So edge dislocation moves by successive and repeated breaking of atomic bonds and which is shifted by atomic distances of half plane of atoms. So in edge dislocation, the dislocation line and the stress are parallel to each other, whereas in screw dislocation, these directions are perpendicular to each other. So then we have the concept of slip. So a slip is motion of dislocations in response to any externally applied shear stress is called as slip. So to define a slip plane or a slip direction, it is the plane in which the dislocation motion occurs. So here you have the figure for edge dislocation and screw dislocation. So here in the edge dislocation, the shear stress is in this direction and the direction of motion of the is in this direction. So the dislocation line and the shear stress both are parallel to each other in edge dislocation, whereas in screw dislocation, it is like the sharing of two planes, steering of two planes. So in here, the stress direction is in this direction and the tearing or the sharing of the atomic planes is in this direction. So here we can say that these two, the direction of dislocation line and the direction of applied stress are perpendicular to each other in the case of screw dislocation motion. So as we have just seen, so slip, the motion of dislocation in result of the shear stress that is applied is can be termed as a slip. So we have slip systems which consists of the both slip plane and slip direction. So slip plane is the plane in which the dislocation moves easily or the slip occurs, and it is the plane with the high planar density, or it is the most closely packed plane. Slip direction is the crystallographic direction along that same slip plane. So here we can also see that the slip direction is the direction with high linear density. So when you have the high linear density, the more number of atoms are present along that line. Hope I'm clear with the concept of slip. So to define the slip systems and the crystal structures, the most commonly are the FCC and the BCC crystal structures. So in FCC, the most common slip system is 111 family of 111 planes and 110 direction. So this 111 plane is the triangular plane which you can see here, which is the densely packed or the most closely packed plane of an FCC crystal structure. And the direction along this is the 110 direction. So in FCC, you have completely 12 independent slip systems possible. Then we have the concept of critical resolved shear stress. Just give me a second. Yeah. Okay, we'll go through this and then see what are the different strengthening mechanisms. So, resolved shear stress is the shear stress in a single crystal. So, when you take a single crystal and you apply force in direction, and this will be the slip plane and the direction. So, here we are taking the angle pi as the direction between the tensile stress and the normal to the slip plane, and the angle lambda as the angle between the tensile stress or the tensile force and the slip direction. So here the critical resolved shear stress is given by F bar over A bar. So it is force over cross section area. As when we resolve the force along this direction, it is F cos lambda, and the area it is A over cos pi. So using this, plugging in this, you can write the equation for critical resolved shear stress as F by A cos lambda cos pi, or simply F by A is the stress that is applied. You can write it as sigma times cos lambda and cos pi. So for a critical resolved shear stress, it is the minimum stress that is required for the slip to occur. So to find the critical resolved shear stress, you can to find the yield strength in a single crystal, it is the critical resolved shear stress over the cos lambda and cos pi. So this cos lambda and cos pi should be the maximum value. So when it is maximum, it is the most. We can say that that slip system is the most favorably or most favorably oriented slip system, and we can say that the slip occurs when the resolved shear stress is greater than this critical resolved shear stress value. And this critical resolved shear stress value will be generally between 0.1 MPa to 10 MPa. So if the shear stress is less than the critical resolved shear stress, then we can say that no slip occurs and therefore there is no plastic deformation in the material. When the shear stress is greater than the critical resolved shear stress, then the tensile stress will be greater than the yield strength, and then the slip or the plastic deformation will occur. So we have seen few problems to how to calculate the yield strength and critical resolved shear stress and resolved shear stress, or how to see the maximum of cos pi and cos lambda in the recitation in the recitation videos before, which were reviewing the homework problems. So you can just quickly go through the homework problems once again. And now in a polycrystalline material, the slip occurs within each grain along the slip systems and that are most favorably oriented with the applied stress. So during the deformation, grain changes their shape and extend in those directions where there is a gross plastic deformation. So for a polycrystalline materials, a slip occurs within each grain along the slip systems that are most favorably oriented with the applied stress. Then we have different strengthening mechanisms. So, so these strengthening mechanisms is generally related with this plastic deformation and the dislocation mobility. So once when if you want to strengthen a material, it is that increase the number of dislocations increase the number of dislocations in the material, or reduce makes this movement of the dislocations difficult, or so that it does not pass and the slip does not occur easily, and then it takes some more time for the material to undergo deformation. So this is the main criteria between the strengthening of metal. So the different or the mainly used strengthening mechanisms in case of metals are the grain size reduction, solid solution strengthening, and strain hardening. So this strain hardening is also called as a cold working. So first let us see the grain size reduction. So to reduce the grain size, uh, so when you reduce the grain size, the smaller the grains, the grain boundary area increases, right? So these grain boundaries acts as a barriers to the dislocation motion or the slip plane motion. So this prevents the slip to occur easily, and the strength of the material increases. So one of the main mechanism for strengthening the materials is reduction, aiming for the reduction in the grain size or to obtain a fine grain structure material. So in result to that, when we reduce the grain size, the yield strength, tensile strength, and the hardness, all these mechanical properties also increase as the grain boundary area increases and the dislocation motion becomes difficult. And to see the dependence of the yield strength on the average grain diameter, it is given by the Hall-Petch equation. So this is sigma y equals to sigma naught plus ky d power negative half. So here sigma naught and ky are the material sigma naught and ky are the material constants, and sigma y is the yield strength, and here d is the grain diameter. And then the next mechanism for the solid solution is the solid solution strengthening. So the strength and hardness of the metal increases with the increase in concentration of the impurity atoms. When you have the plain or the pure metal, it is like a pure metal does not have much of the dislocations, right? So when you have impurities induced in that material, the dislocations increase. So as the dislocation increases, the movement of the slip becomes difficult, and the material can get harder, stronger, and the yield strength increases. So inducing or addition of impurities, which is also called as solid solution strengthening, is the other mechanism where we can strengthen the material. So here you can have these compressive stresses or tensile stresses in the tensile strain material. So and here, based on the graphs we have, standard graphs we have, seeing on the material nickel and copper, it can be defined that the yield strength is directly proportional to the concentration of these impurity atoms uh, per time power half times. So sigma y is directly proportional to C half, where C is the concentration of the impurity atoms and sigma y is the yield strength of the alloy. And then the other main mechanism for strengthening of these metals is the strain hardening. So this is also called as cold working. So cold working is just working on the material or deforming the material, like it is like applying stress on the material at room temperature or at room temperature. So this is called as cold working. So when we strain them, it is like inducing strain in the material and little changing the uh, grain structure. So this strain hardening is inducing strains in the material. So for this purpose, it is just a cold working. So the material is passed through rolls. So this on by passing through the rolls, compressive stresses are applied on the material, and so it undergoes the change in diameter and the inch in length, and then different dislocations are applied in this material. So the deformation, so the slip motion of dislocations becomes difficult, and the materials become harder, and the yield strength increases for the material. And to calculate the percentage of cold work, it is given by the formula A naught minus AD over A naught times 100, where A naught is the original cross section area and AD is the deformed cross section area. So during the plastic deformation, dislocation density increases. The distance between adjacent dislocations decreases because the strain field interactions and the dislocation moment of dislocation is arrested or is restricted. So, and the materials become harder and stronger. So here is a small graph which shows a strain, which shows with the percentage cold work. We can see that as the percentage cold work is increases or as the strain hardening increases, we can see that the yield strength of the material is increasing. So here sigma y is increasing. Sigma y for 24% cold work is greater than the 4% cold work, which is greater than the 0% cold work material, which you can see here. It is shown by the red arrow. And as you strain harden the material, we can see that the yield strength and the tensile strength of the material increases, but whereas the ductility or the percentage elongation of the material decreases. As it becomes more harder, it is difficult to uh, deform or elongate, so the ductility decreases. And to calculate the dislocation density, it is given by the total dislocation length over the unit volume. Here are a few problems, and we have seen few problems like how to calculate the percentage cold work and using the Hall-Petch equation in the homework solutions. And then we have the process of heat treatment. So when you do heat treatment, it is like recovering the material. So all the previously cold work or the change in the structure strains induced in the material can be removed by giving a treatment called as annealing. So this annealing is defined as heating the material to a particular temperature so that all the effects of the strain hardening are removed. So annealing temperature it can be defined as the temperature at which the grain structure is completely refined with 1 hour treatment. So there are two steps or the three main stages in annealing, which is recrystallization, recovery, recrystallization, and grain growth. So in the recovery stage, first initially when the material is heated, all the physical properties that are lost in the material, like any thermal conductivity, electrical conductivity, any magnetic properties, all these are recovered in the first stage of annealing. Where the second stage of annealing, which is the recrystallization, the complete grain structure is completely replaced with a new set of grain structure. So it will have newly formed equiaxed grains, randomly oriented equiaxed and strain-free grains, which are the finer grain structure. And then by giving some time for that and at the particular temperature, these grains that are formed will grow in size and the grain growth occurs. So in the recovery stage, all these properties are gained back due to the diffusion and the removal of the dislocations due to this diffusion process at the higher temperatures. So here you can see the microstructure. So this is a cold work material, and then it is after recrystallization, you can see a new set of small grains have formed along the high energy grain boundary regions. And then we can see that the recrystallized grains increases and the microstructure is completely replaced and you have a new microstructure now. So previously this was the microstructure that we have, but now it is completely replaced. So here you have a finer and equiax randomly oriented grains. So this is the recrystallized microstructure. And then after the recrystallization, when you have cold working, these grains increase in size, so the grain growth occurs, and which may result in a microstructure which looks like this. So this is after 15 minutes of stage. So the average grain size increases here, and the grains continue to grow. And then to stop the annealing process, we take out the material at this temperature, and then we cool it in air. And to see what is the influence of the grain size on the properties of the material. So materials having small grain size are relatively strong, tough, and then are harder. Whereas the materials which have large grain size are like more ductile, have good creep resistance at higher temperatures, and then are relatively softer. And the dependence of the average grain size with the time is given here by this equation. Here this is a exponent, and generally it will be equals to 2. So these are the 3 stages of the annealing. So here first, when you have the cold work material, all the dislocations are removed, and then you'll have in the recovery stage all the due to diffusion all the dislocations are removed, and then all the physical properties of the material are restored. And after that, in the recrystallization phase, all the this grain structure is completely replaced by a new set of grain structure. So a small tiny equiaxed grains starts forming at the grain boundary regions, and then the more number of grains are formed, and completely the microstructure is replaced with a new set of grains. And then in the grain growth stage, slowly as the temperature is maintained, these finer grains increase their size and grows to a increased average grain size diameter. So recrystallization temperature is the temperature at which this microstructure can be completely replaced when treated for a 1 hour time. So this recrystallization temperature will be like a 0.4 to 0.7 times the melting temperature. Hope I'm clear with this. Now let us see these failure mechanisms. So here for failure, we have mainly 3 types of failure. One is the fracture, and then we have the fatigue failure, and then the creep. So in fracture, we have 2 different types of fracture. One is the ductile fracture and one is the brittle fracture. So when you have these metals generally undergo ductile fracture. So here, before undergoing fracture, the material deforms to a particular extent, and then it permanently deforms, which is generally seen in the metals. So in ductile fracture, the crack propagation is slow, and we have a significant plastic deformation that is occurring. So if we can see that it has an indication or a warning that the material is undergoing some deformation, and then it fractures eventually with some time and stress applied. Whereas in brittle fracture, we don't have any indication of failure. It just permanently deforms or just fractures into different parts. Here there is rapid, once the crack is initiated, it propagates and it cracks. Whereas in ductile fracture, once first the crack, a small crack or something like that initiates, and then it has a slow propagation, and then it sees the failure. So in ductile materials, where there is ductile fracture, there is necking in the material. So there is a formation of a cup and cone in the tensile test. Whereas in brittle fracture, the surface is flat and perpendicular to the direction of the load applied. So here you can see here the material is first elongated before it undergoes fracture. So this is a, we can say that this is a very ductile material. Here there is a small grooves that are formed and the material is elongated before it undergoes fracture. So we can say that this is moderately ductile. Whereas in a brittle fracture, this is the fracture surface is flat and this will be perpendicular to the direction of the force applied. In ductile fracture, first when there is a small crack that is formed, so these cracks combine with each other, their coalescence, and then the crack, after initiating the crack, it takes a certain time for the crack to propagate, and then the material undergoes a certain amount of deformation, and then the material undergoes fracture. And this is the cup and cone surface for a ductile material. And in brittle fracture, we have two different types of crack propagation. One is the transgranular and the other is the intergranular. So this transgranular crack propagation is that the crack propagation is between the grains. So it goes through the grains. Whereas in intergranular crack propagation, this goes between two grains. So this is like it generally goes along the grain boundaries. Whereas here it goes through the grains. So from one grain to another grain, it goes like this. Where this in between two grains. And then to calculate the stress at the crack tip, so suppose if we take a material and it has an internal crack. So this internal crack can be has a length of 2a. And if we had a surface crack, consider this length as a. So the stress at the crack tip, it can be written as 2 times sigma naught times a over rho t power half. Here sigma naught is the applied stress and rho is the radius of curvature of the crack. So this is the radius of curvature of the crack, and A is the crack length. So if it is surface crack, then you can take the surface crack length as A. But if it is given as an internal crack, so that it is that you are given the value of 2A. So from 2A, you need to calculate A and then put it in the equation to find the stress at the crack tip. And then to calculate the stress at the crack tip, when you have the specific surface energy and the modulus of elasticity, then you can use this equation. So sigma c is equals to 2e times gamma s over pi a whole power half. So here E is the modulus of elasticity, gamma s is the surface energy, and a is the half of the internal crack length, is the length of the surface crack. And here the crack propagation occurs when the sigma m is greater than the sigma c, where sigma c is the critical stress for the crack propagation. And then we have the concept of this fracture toughness. So the fracture toughness of a material is indicative of its resistance to brittle fracture when a crack is present in it. So to calculate the fracture toughness, it is given by Kc equals to y sigma c times root pi a, where Kc is the fracture toughness and the units are MPa root m. Y is the dimensionless parameter, which is the extent, and sigma c is the critical stress for the crack propagation, and a is the crack length. For most of the materials, y the dimensionless parameter will be equals to 1. And in this, you have different modes of crack propagation. So based on the mode, it is defined as K1C. So this mode 1 is the opening or the opening mode, which you can see in the figure here. And then we have other modes, which are the tearing mode and the sharing mode. Once you have the critical stress and you know the fracture toughness value, you can also use this equation to find the critical stress. So critical stress is KIC over Y pi A. It is just rearranging the formula above. And then the next type of failure mechanism that we have is the fatigue. So fatigue is a common type of catastrophic failure which occurs when the applied stress levels are fluctuating with time. So there are three different types of stress cycles. One is the repeated stress cycle, one is the random stress cycle, and the other is the reversed stress cycle. So it is a reverse stress cycle where you have a maximum and minimum of the stresses, and then there is a repeated stress cycle which undergoes same fluctuations in the stress level after a period of time, and this is a random stress cycle where the maximum of the tension and compression are different. So when you have the maximum and minimum of the stresses, you can calculate the mean stress, the range of stress, stress amplitude, and the stress ratio. So the mean stress is calculated by the formula sigma m equals to sigma max plus sigma minimum by 2. And the range of the stress cycle is the difference between the maximum stress and the minimum stress. And the stress amplitude is the range of the stress over 2. So this is sigma max minus sigma minimum by 2. And the stress ratio is the minimum stress over the maximum stress. And then to SN plots are describes the fatigue data. So here S is the stress amplitude and N is the number of cycles to failure, and which N is generally taken in a logarithmic scale. So there is a endurance limit or the fatigue limit, which is given by this line here. So from where the stress amplitude remains for a stress amplitude, when the number of cycles to failure remains constant, such that point can be called as the saturation limit or the fatigue limit, which is given by SFAT. So when the stress amplitude is below this limit, we can say that the material does not fail identically or it has a infinite number of cycles to failure. But when the stress amplitude applied is above this, we can say what respective number of cycles to failure. So fatigue strength, it is the stress level at which failure will occur for some specified number of cycles. Suppose if you have this one. So to calculate the fatigue strength, so we can say that we can just go through the curve here and then drop the perpendicular to this y-axis where it shows the stress amplitude. So for these number of cycles at this stress, the materials fail. We can say like that. So to calculate the fatigue, it is the total number of stress cycles to cause the fatigue failure at a specific stress amplitude. Suppose if we have this S1 stress. So at this stress, the material undergoes failure after the particular number of stress cycles. But when the stress cycle, when stress amplitude is below the fatigue limit, we can say that the material does not fail, or the material may fail after infinite number of cycles, or it has a larger fatigue life. So by reducing the magnitude of the mean stress value, we can say that the fatigue life improves. And then the other mechanism of failure is the creep. So here creep is the time-dependent plastic deformation of metals subjected to a constant stress and at a temperature which is greater than about 0.4 times the melting temperature. So this type of plastic deformation or failure is called or defined as the creep behavior. And to calculate so the creep undergoes in three stages: the primary creep, secondary creep, and the tertiary creep. So it is the strain over the time. So where it initiates, it's the primary creep, and then it slowly increases, and then after a certain amount of time, it undergoes a fracture. And then we have a formula also for calculating the steady state creep. So this is given by epsilon s, which is the creep strain equals to k times sigma power n exponential minus qc over RT, where Q is the activation energy, R is the universal gas constant, and T is the absolute temperature. So you can use that formula to calculate the creep strain, steady state creep rate. Hope I'm clear with the concepts. Have any more questions, or if you need any more detailed explanation, or if you need any more practice problems, or any doubts regarding the homework problems, you can log in back to the recitation and we can discuss it. Thank you so much, and I wish you all the best for the class test 3. Thank you.